8.1 distributions of the sample mean. So let's describe the distribution of the sample mean. And normal population will be the center and spread. Um, so sampling distribution is the list of all possible sample means of size n from the population. So if we want to survey all of America for qualitative data, we can't survey 300 million people. That's impossible. Or it would be super extensive and would cost a lot of money. Um, so we use something called a sampling mean distribution, which is simply us calculating means from things of different or things of same sample sizes and getting a large things and making a distribution of it. So let's go over to Sketchpad here. And there's 300 million people in America, so 300 times 10 to the 6. And basically, we can't survey all these people, so we'll survey groups of any people we want. And we could do 9 people. And we'll get to the central limit theorem later, but it states that as there's a higher amount of frequency or higher amount of basically trials in each one, there's gonna be a higher or a more normal distribution, and we'll get to that later. But so first, it's important to note that we find the mean of each sample, then we graph it on a thing with the means times the densities. And we use the densities and the means when trying to use kind of like a standardization, which we'll get to a little bit later. But simply put, we calculate the mean of each sample and then we plot it all over here. And we use the formula that we've gotten before to basically make a probability distribution. So that's all that means. And the standard deviation is the same thing, but it's the standard error of the mean, meaning how much each mean tends to deviate, or how much, or just standard deviation of the data set. So how much error there is in the total data set from the actual mean. So the reason why a mean distribution looks like a normal distribution, this is because most means center around the actual mean, that is typically the average. So let's say let's say that out of 10 people, 4 tend to like ice cream. So that means 0.4 is the average amount. Every point, every person, there's 0.4 people that like ice cream. So when we graph that on a probability distribution graph, and we do sampling means, and we take means of sample size of 9 and another sample size of 9. On average, most people will contribute 0.4. So 0.4 or 40% of people will like ice cream. So that means that on average, most people will be around here, which is the mean. And as we mentioned before, if it's a normal distribution, the mean is equal to the mean and equal to the mode, which means the highest point over here will be the median. And then we'll do the inflection points, which is plus or minus the standard deviations. Or right here would be the mean, the error of means, which is what it's called because we're making a distribution of means. And we can use the means because it is more accurate than a sampling distribution or probability distribution graph, and I'll explain why in a second. So take this as a population. And when we have so many points ranging from 0 to 900 or whatever, the distributions can be widely spread apart. However, if we do means or averages, if we get a super high data point, so like let's say that there's someone that turns out to be and turns out to have like $800,000, and let's say this is a graph of how much money people have, and this will be around the 800 mark. So let's say someone has $800,000. That's pretty rich. However, that just means that there's more deviation. This will contribute to more deviation. However, if we calculate the average of 800 plus some other standard data points, and then plus a low outlier, so like let's say someone makes 100 grand in their lifetime, that will be 800 grand plus 100 grand. And the average between those two cancel out to make a more equal mean or average. So simply put, the means become tighter as opposed to this whole graph because high outliers and low outliers cancel each other out, and the density remains the same. So it's the same concept from the other general probability distribution graphs, but means are more tight together, and you'll never get a mean of like 1 because most, on average, are not outliers. So that's kind of what the logic is behind that. It's a little bit abstract to understand, as much higher statistics is. So why are distribution sample means are important? So this is the same explanation. Take two sample means. Let's say for one trial we have an average between 100 IQ and 60 IQ. The average would then be 80 IQ because 100 plus 60 divided by 2 is 80 IQ. The lower IQ brings the 100 down, so the 60 IQ brings the average, or brings the 100 down. So now the average is 80. Now take another one with an average of 100 and 140 IQ. The average would be 120 IQ. Both have outliers. However, averaging them makes the smaller 60 IQ right here cancel out the greater effects of the 140 IQ because of the mean distribution. Simply put, sample means are more stable than regular ones, and they're tighter and more compact because you'll never get a mean of like 0 when you can have a data point of like 0. So that's what the logic is behind that. So why does it look normal? So it's important to note if the original population is normally distributed, then the sampling distribution of the sample mean is also normal, no matter the sample size. If it is not normal, the central limit theorem tells us the sample distribution becomes normal as the sampling size increases. So take those 300 million Americans again, and we have a sample size of 9. The issue here is that this is highly unstable. If we get like even all constant ones, so like let's assume that there's 8 data points that are pretty constant and consistent, but now we get a huge outlier, and let's assume it's a very huge one. This messes it up. However, as the denominator gets larger and larger, which is basically like the law of large numbers, the outliers have less and less of an effect, and therefore the outliers aren't considered inside. The distribution becomes more normal because it eliminates outliers and brings it more towards the central tendency, and that's where the other idea is derived of the mean equaling the sample mean, or the average of the sample means. So means of the sample means is the mean of so the mean of all the sample means is equal to the mean. I think I know the logic behind that, but I can't really explain it because I don't know like the algebraic way to explain it. But I feel like I understand the logic, but I can't really say for sure because I'm not a statistical professor or anything. But basically what that means is if we have a sample of 30 and we take samples of 30 and 30 every time, it's important to note that the average over here plus the average over here and the average of all the sample sizes divided by the number of samples you have won't be equal to the mean. So whenever it gives you the mean of the population, we can assume that's also the sample average of all the means of the samples. So it's a little bit easy to understand. So if we have groups of 30 here, groups of 30 here, groups of 30 here, groups of 30 here, and let's say the average or the mean here is x1, the mean here is x2, the mean here is x3, and the mean is x4. x1 plus x2 plus x3 plus x4 divided by 4 is going to be equal to the actual population mean. And we'll label that as that. That's actually a sample notation, but I guess we'll just use that. So yeah, that's what it's basically saying. The average of all the sample means will be equal to the mean of the actual population. This is the standard error, which is basically the standard deviation. I'm not sure how that formula was derived, but the formula is the standard deviation of the population. So we'll do standard deviation divided by the square root of the sample size. And that will give you the sample size of, or that will give you the standard error of the mean distribution. So that's how it works. I'm not really sure how that works, but the standard deviation of the sample means it gets smaller, sample size increases because it then more approximates the mean, as the average of all sample means is equal to the mean. So all that means is that the higher sample size, the less outliers contribute, and the more they cancel each other out, and therefore it's more compact and has less standard error. So same formula, z-scores would be the sample mean minus actual mean divided by standard deviation of sample means, and you can use a graph to approximate this. You can use a graph to calculate the probability distributions. So if you get like a mean, so let's say we measure another group of 30 people and we get their mean to be a certain score. We can check if that score is an extremely rare score by using the probability distribution graph. Or we can just use like the empirical rule, which is, I guess, a little bit easier, but it's a rule of thumb. It's better to use an actual chart, which uses calculus and other tools to calculate the probability density. So yeah, that's literally it. So the difference between the two is that means are more stable and more compact. But other than that, the probability distribution graphs are equal to the mean distributions, the sample mean distribution graphs. The sample mean is equal to the average, or the population mean is equal to the average of all the sample means, and the standard deviation of the sample is equal to the or the standard error of the means is equal to the standard deviation of the population divided by the square root of all, or the number of the sample size. So thank you.